Mic off.
This thing's kind of slow. Okay, now it's starting. Okay, hopefully you could see a black screen with yellow letters. Okay, so announcements. The labs for this week are experiments 19, which started today, and 20 will be on Wednesday. And then the last week's lab 17 and 18 are due tonight by midnight. And the next exam is on Wednesday. It'll be posted on Blackboard by 8 a.m. Oops, before I forget, I should go back and record this.
Mic on.
I already have my recording started as well.
Okay.
Mic off.
Well, somehow I can get out of this and get back to the first screen. Okay. So here I'll turn recording on and start over. Okay. So the next exam is on Wednesday. It'll be on Blackboard by 8 a.m. and due by midnight. And it will cover chapter 16, the class notes and OpenStax. This chapter 16's on thermo. And then it will also cover most of chapter 17. It'll cover parts 1 through 3 of the class notes, which are posted on Blackboard, and the related parts of the OpenStax chapter 17. And the questions relating to KSP and pH are deferred to the next exam. That should say, instead of and, it should say are. Yeah, so those particular parts of chapter 17 are the more advanced parts pertaining to KSP and pH. So those will be on the next exam. So study chapter 17, all of the class notes on Blackboard, and there are 3 parts, like 3 separate PDFs posted, 1 through 3, and then the related parts of the OpenStax chapter 17, and all of that excluding KSP and pH. And the class project, which is due Friday, May 8th, now has all the information on Blackboard. I put an Excel file up there in the class project folder. We'll have a look at that in a couple of minutes. And there's an upcoming assessment. It's a second departmental assessment, and it has to do with writing skills. And it will be optional and worth some extra credit, and all of the details are to be determined. So I'll let you know about that probably sometime this week. Okay, now on the labs due or upcoming, do any of you have questions? I'll wait a moment here in case somebody has to think of a really tough one to ask. Okay, doesn't sound like there are any questions. Okay, so before we get started with chapter 17, let's have a look at that Excel file. Okay, this is what's posted on Blackboard. This is there are 5 tabs in it. there's a main tab which contains the initial graph, and this is a part you'll be working in the most. And, you can edit this however you want. And the second tab is amino acid formulas. This is just a list of the 20 amino acids and their linear structures. And in this code, the code in column A, like all A, R, N, D, and so forth, correspond to these structures in this column here. So those two columns are pulled over here in columns A and B in this sheet. So see this, I click on the first code, which is A in cell A5. And if I go up here in the formula bar, it says it's pointing to the tab named amino acid formulas, which is down here, cell A7. So if we click on that tab and go to A7, see there's the A. And the code is then row 7. And I guess this will be A, B, C, D. I guess this is a merged column. So if we go here, or no, it says it's pointing to amino acid formulas, cell E7. So E7 apparently points to that column with all the formulas. And I've currently copied over 8 formulas, and this little sheet is working for 8. And you can see how it works by changing things and watch how the graph changes. And to get the other 20 in there, just copy and then paste. Like if you wanted to add the 9th one, copy paste, see, and it'll put the 9th one. If you want the next 2, paste like that, and on down till you get all 20. And this stuff here would have to be moved down if you want to accommodate all 20. Okay, and then the COVID-19 spike protein data is in this third tab, and all of this stuff here is reference information from where it was pulled on the web. And this is a sequence, 1,250 something codes or amino acid residues, actually 1,273. And this is a continuous string. It's the same set of codes, only one long string. And then to work with this in a sheet, we really need those codes in a column. So this row 38 is transposed into columns here in cells 41, 42, and so forth, all the way down to the end. And by the way, to go quickly to the end of a column, use the end down arrow. It'll go all the way to the end. If you want to go to the top, hit end and up arrow, and it'll go to the top. So this column here, 1,273 codes, will eventually be pasted right here. So you'll have 1,273 codes listed. Then you'll need to copy this formula, which is, it just basically translates that alphabetic code into a number so that we can compare it numerically. And then the protein sequence that you look up will get pasted here. And it's in red, and then you'll copy paste this code formula down. So all of this will be filled like down to 1,200 and something rows. And then along with this is a difference. It takes a difference. It takes this code, the blue code minus the red code, and writes a difference there. And this formula, which gets copied down, basically looks at this column, and if it finds a 0 there, it writes a 0. If it's not 0, it'll write a 1. So there's only 2 possible values, 0 or 1. And then these are what get graphed here in this graph. If there's no difference, it's a 0. If there is a difference, it's a 1. and the actual residues get pulled from here. You match the code to the formula. So basically it's searching, it's looking in cases where there are differences. It looks in the blue codes here, like the first one's A. And since there is a difference, it writes a formula for A, which is here, and the formula for your protein, which here has a test value of R, and puts a formula for R there. So see, the formula for R is also here. It's pulling it out of this cell. And let's see, does anyone have any questions so far? Can someone make a noise so I know I'm not unhooked?
Yeah. No, I don't have
Okay.
any questions so far.
Okay, thanks. All right, so if you look here and at the formula bar, see that looks kind of complicated, and it'll look even more complicated. In fact, you'll have to expand this formula bar down to even look at it. This handles 8, and you'll need to upgrade that to 20. And how you do that is by working with the logic in these if statements. And here's an example. How about if I put a 1 here, and then, and in this column, let's say, want to say if I9 is equal to a 1, then I want to write car. If it's not a 1, I want to write, how about a train? Just making this up. Okay. So see the if formula has 3 parts. The first part is the condition.
Mic off.
This condition is cell I9 equals 1, which it is. The second argument is what to do if it's true. In this case, if it's true, replace or write the word car. Otherwise, write the word train. So see, so it's seeing a 1 here and writing car. So what if I put a 2 there? It should write train. 3 train, or negative 111. 0 writes train. The only way it'll write a car is if there's a 1 there. So we can extend that. So what if let's add to this. So if it's a 1, we'll write a car. Let's see, let me check this one over here first. Okay, so yeah, we need to replace this. So let's say if we want to embed something like if I9 is equal to 2, write about a go-kart. Otherwise, write boat. There, so now we have multiple conditions. So if we have a 1, it'll write a car. If it's not 1, it'll check if it's a 2. If it's a 2, it should write a go-kart. So let's test it. Put a 2 there. It writes go-kart. we put a 3, it should write boat. You write a 5, it should write boat. Negative something. Yeah, so that's a sort of thing that needs to be done whenever updating these formulas here. It's a bunch of embedded if statements. So go to the end here, and it's easier to do this in Word, like take this formula and paste it in Word and do your edits and then paste it back. But this quotes is where the next condition goes. So you copy one of these like this, copy it, and then paste it over the quotes. That. And keep doing that until all 20 are coded. And then once that's done, you'll be able to scroll down here, and anytime there's a difference, you'll be able to see what the actual structure is. And to find something related to COVID-19 or SARS, check out these databases like Uniprot or BLAST. The links are here. Just enter in some search term like SARS-CoV, and you'll see things pop up. It'll ask if you want human or bat or mouse or whatever, various influenza viruses. Just pick one that's somewhat similar to the COVID-19, and you might have to insert blanks. And by the way, this COVID-19, see, they put blanks in the first 9 spots and then 4 more a little later. So like these all here where they're vertical hash marks, those were actually blanks, and they put blanks in there to line it up with the SARS protein. Okay, but so that's the basics of it. If questions pop up, let me know. Okay, so let's go back to electrochemistry. Okay, we're in part 3. Those notes are on Blackboard. And it starts off with the review of some of the balancing methods. Since we're in electrochemistry, we're balancing in acids and bases. And these are redox reactions, and we need to split them into half reactions to to describe, for instance, how a battery works, where we have a half reaction on the anode and the other half reaction in the cathode. So here's the reaction we need to balance. So the first step is to identify which elements or compounds are similar left and right. Like here we have copper on the left, copper on the right. So those two would belong in one half reaction. And then the nitrogen and oxygen also occur, and they go together in their own half reaction. So we'll split this into 2 half reactions. Those are the 2 half reactions. And then let's start over here with the copper. Copper, left and right sides are identical, except for charge. All we need is to add 2 electrons on the right to balance it out. So the half reaction is finished at this point for the copper side. Now let's look at the nitrate side. It looks like we have 3 oxygens on the left and only 1 on the right. So we add oxygens through water. So we add 2 waters to the right. That gives us our 3 oxygens on both sides. And that also introduces 4 hydrogens, which are unaccounted for. So we add those to the left as H pluses because this is acidic solution. So there are H pluses present. So the reaction would use 4 of those. So at this point, it's balanced with respect to nitrogen, oxygen, and hydrogen, but not with charge. The right side's neutral and the left is a +3. So we need to add 3 electrons on the left to balance that out. So those are our 2 balanced half reactions. And we put those one atop the other like that, because we'll be adding them. And the top one requires 2 moles of electrons, whereas the bottom requires 3, and we need to even that out. So we multiply the top reaction by 3 and the bottom by 2. When we do that, first reaction scaled by 3, so we get 3 coppers left and right and 6 electrons. And then the next reaction is multiplied by 2, and we also get 6 moles of electrons. By the way, the 6 moles of electrons comes up whenever we talk about N. For example, in equations like delta G equals minus NFV0, the N in there is moles of electrons, and that corresponds to the 6 here in this reaction. So it's one of the reasons we have to do half reactions, is to figure out how many moles of electrons we have. So at this point, we can add the 2 reactions, and we end up with this. We have a balance left and right, and now let's look for things to cancel out. It's like we have 6 electrons left and right, which can be canceled out. And there isn't anything else. So this would be the finished overall reaction. It's balanced. So that's an example of how we would balance a reaction in acidic solution by the ion electron method. So let's try another one that's a little more involved. Okay, here you have As2O3 and nitrate. And let's split that into 2 half reactions. So you have As2O3 and it's arsenic acid. And the other half reaction involves nitrate and N2O3. So let's balance the left one here for starters. Looks like we have, firstly, we have 2 arsenics on the left and only 1 on the right. So let's fix that first. So we put a 2 in here. Now let's balance with respect to oxygen. We have 3 oxygens on the left, 8 on the right. So we need to add 5 waters on the left to get the oxygens to match. So now let's look at hydrogen. We have 10 on the left, 6 on the right. So we need to add 4 on the right as H pluses. So now it's all balanced with respect to the elements. So check the overall charge. Looks like everything's neutral except for these 4 H pluses. So we add 4 electrons to the right to get the charge to balance. So this is a finished half cell reaction. Now let's look at the other one. This one firstly needs nitrogen balanced. So we put a 2 on the left. Now it needs oxygen balance because there's twice as many on the left as the right. So we added 3 waters on the right. Now let's add 6 hydrogens to the left as H pluses. And now it's all balanced with respect to elements, but with charge, we have 6 plus on the left and 2 minus also on the left, which makes 4 plus. The other side's neutral, so we had 4 electrons on the left to balance the charge. So this is a second balanced half reaction. So now let's stack them on top of each other like that so that we can add them. And looks like they both involve 4 moles of electrons, so we don't need to scale them by any multiplied factors. We can add them straight. So if we add them, this is what we get. And now let's look for terms we can cancel. We have the 4 electrons, which can go away. Then we have 6 hydrogens on the left, 4 on the right, so we can get rid of the 4 on the right and change the 6 to a 2 here. And we also have waters, 5 on the left, 3 on the right. So after we cancel out everything we can, we end up with the balanced overall reaction, which looks like this. Okay, so let's have a look at the next one. If you have questions, be sure to go ahead and interject. This is, let's see, number 3. This occurs in basic solution. The other 2 were acidic. This one's basic. And the method we use to balance in basic is exactly the same as what we've done already, except for the last step, which involves replacing or adding hydroxides wherever we see an H+. So let's proceed exactly like we did before. Split this into 2 half reactions. There are 2 half reactions. Balance the left first with, make sure there are 4 ammonias on both sides. So we put a 4 there on the right. I'll go a little faster through this one since we've already done 2 examples. So that's our balance reaction here on the left. The other half reaction balances like this. Now let's stack them up. We have 2 moles of electrons in both, so we can add them directly. So now we cancel out like terms, get rid of the 2 electrons. But here's where we have an extra step compared to the acidic method. Anytime we see an H+, we add 4 hydroxides to both sides, because where this reaction is occurring in basic solution, so there is no H+ there, or very little of it, but the OH- is in great excess. So get rid of the H+ by adding an equal number of hydroxides. So that will give, here on the right, that'll change 4 H+ to 4 waters. So that's where these 4 waters came from. And then the 4 OH- were also added to the left side, so they appear here. So now we have 2 waters on the left and 4 on the right, and we can combine those to get 2 on the right, and that's our finished overall balance reaction. So see that the 2 methods are the same except for the very last step where you replace or you add an equal number of hydroxides for every H+ that's present. Okay, so let's go on then in chapter 17. These slides are from Jesperson. Let's look at predicting whether or not a reaction is spontaneous. So for any redox reaction, we can calculate E0 for the cell, and we'll come up with some number. And if that number is positive, then the reaction is spontaneous. And if, on the other hand, the E0 is negative, then the reaction is not spontaneous. And that's equivalent to saying that the reverse reaction would be spontaneous. And the reason we look for a positive E0 is because E0 is related to delta G through an equation. It's delta G is equal to negative NFE0. So there's a negative sign in that equation. So the sign is inverted. To have a spontaneous reaction, we have to have a negative delta G. And because there's a minus sign that I mentioned, that means E0 has to be positive. So negative delta G is the same as positive E0. And the 0 means specifically it's measured at 298 Kelvin, and all of the ions are in a concentration of 1 molar. Or if it's a gas, the partial pressure is 1 atmosphere. And a galvanic cell, that is a battery, is always spontaneous. And the reason is it's set up to be spontaneous. It's like a battery wouldn't be very useful if it was a non-spontaneous reaction. So let's use E0 to predict spontaneity. So let's look at this reaction and figure out whether or not it's spontaneous as written. So here's a redox reaction, and we know it's occurring in acid because of the presence of the H pluses. So this is split into 2 half reactions. And for the first one involving iodine solid being converted to iodide, E0 is plus 0.54. And for the other one, E0 is plus 1.44. So the side with the more positive value would be where reduction occurs, that is, it gains electrons. The other would be the oxidation, it would be the reverse of the top reaction. So if we take the difference, the reduction versus the oxidation, we get 1.44 minus 0.54 volts. Here that Jesperson takes a difference, but I always like reverse this one, and that reverses the E0, and then we add them, so we add a negative. But you can do it that way, or by Jesperson's way, he subtracts out. He says cathode minus the anode, reduction minus oxidation, and he keeps the same positive sign there. Either way will get you a 0.9 volt spontaneous reaction because it has a positive value. So let's look at this one. Let's determine whether or not the following reaction is spontaneous as written. Here we have gold, solid gold, reacting with aqueous aluminum, converting to aqueous gold and solid aluminum. Just FYI, gold's about the most stable metal there is, except for maybe platinum. So it's very unlikely that gold solid is going to ever change into something else. Certainly not because aluminum's there. Gold's really stable. So this will definitely be non-spontaneous. But let's go through the steps to prove that. So we have aluminum. Its reduction potential is minus 1.66 volts. Gold's reduction is plus 1.50 volts. So let's arrange those in terms of oxidation and reduction. Calculate E0 with a cell, and we get minus 3.16 volts, which is a very large negative number for E0. So this would be non-spontaneous. Okay, so let's look at this set of reactions. The top reaction is the overall. Second and thirds are the half reactions. The first one has an E0 of 1.77. Second has an E0 of 0.45. Okay, so what's your prediction? Is it A, B, C, or D? Any takers? How about Maddie? Are you there?
Mic on.
I'm not really sure, but I think it's B.
Okay, because that's 1.77 minus 0.45.
Yeah.
Okay, let's see if you're right. Yep, you're right.
Ooh.
Yeah, so the more positive one is the 1.77, so we reverse the other to make it an oxidation instead of a reduction. That flips the sign. So we end up with 1.77 negative 0.45. It comes to 1.32 volts, which is positive and therefore spontaneous. Okay, another application of electrochemistry is finding the equilibrium
Mic off.
constants. We've gone over some of that last time, but let's have a look here. Here we have delta G, which is equal to minus RT ln K. This popped up in chapter 16. In chapter 17, we have delta G is equal to minus NFE, or and some moles of electrons, and F is a Faraday constant. So we can set those two right-hand sides equal to one another and come up with an expression that relates E0 to the equilibrium constant. So let's calculate Kc for a redox reaction. Okay, how about this one, where E0 of the cell is plus 0.9 volts. So first we need to determine what N is, N's moles of electrons, and to do that we go through the half reactions, find out how many moles of electrons are needed, and in this case it's 6. So N is 6, and we have a 0 there on the E. It's E0, meaning 298 Kelvin. So the temp's 298 Kelvin. The gas constant R is 8.31 joules per mole Kelvin. So let's plug all that into this expression. And you end up with this. So natural log of Kc is 210.3. And if we take the exponential of both sides, get e to the 210th power, which is 2.1 times 10 to the 91th power. So that's a really gigantic number. So it's K is a really large number, meaning it's very spontaneous. So our answers here are the E0 was given as 0.9 volts positive, and its positive sign told us it was spontaneous, which would imply that K is a very large number, which it is. And the delta G is a negative large number, which it is. It's minus 521 kilojoules per mole. Okay, so let's look at this one. Here we have to determine Kc for a reaction that has a standard cell potential, or E0, value of plus 2.55 volts and transfers 4 electrons. Okay, what is the equilibrium constant? So this would need to be plugged into a calculator. So anyway, the answer turns out to be D, 3.9 times 10 to the 86. And we would have found that by using the same expression. We have, here's the Faraday constant, 4 moles of electrons, and so forth. And anyway, so we ended up with 4 times 10 to the 86. Okay, so were there any questions? Okay, so let's go on then in the class notes part 3. We've been following along We did the first 3 examples. This is the 4th example. Okay, this has to do with spontaneity under standard conditions. So for this reaction, let's calculate E0 and delta G0. So first, let's write down the standard reduction potentials for silver and chlorine. So the way those pop up in the table, silver ion is reduced, yielding silver solid. That's 0.8 volts. And then chlorine gas is reduced to chloride ion, and that has a reduction potential of plus 1.36 volts. Now, the goal of this is to manipulate these reactions in such a way that we end up with the given reaction.